The first lecture is going to start off being a bit of an introductory waffle about why we care about chemistry anyway, and this year is the International Year of Chemistry. You probably didn't know that, but it is. And so it apparently behoves all of us chemists to wave the flag and sort of preach the propaganda, if you like, about why chemistry is such a wonderful thing. So I want to do that just for a little bit at the start. And then what we're going to do for much of today's lecture is do some very basic stuff. And for a lot of you, this may count as being revision, but I've been doing this game long enough now to know that a lot of people know a lot of the stuff up here, but a lot of those people don't know the stuff underneath, the really foundational stuff. And they've always just kind of pretended that they knew it, and up till now that's been fine, but at some point if you don't have that foundational stuff it kind of catches you out. So today's lectures might be a little bit of revision for you, but I promise you it will get harder quickly enough. Right? So if today's sweet, then just enjoy it while you can. Yeah? So what we're going to do in this course is hopefully start to look a bit at how these different chemical elements, when they are combined into compounds, have particular properties which we can try and understand from very underlying foundational ideas. Right? So today we're going to talk about things like atomic structure and electron configuration and this thing called the stable octet rule. These sorts of very basic ideas can allow us to understand lots and lots of the properties of the elements and the compounds that we come across in the world around us. Right? He mentioned that one thing you can do with zinc, and you may well have done this at school at some point, is you can throw it into hydrochloric acid and you get hydrogen gas given off. Yeah? And so you get this pop test thing where you do in a test tube, you put your thumb over the top, and then you let it go with a little match and it goes pop as the hydrogen that's evolved by that reaction explodes. A very similar chemical reaction was used by a guy called Jacques Charles in 1783 to make enough hydrogen to fill up that balloon. Right? This was about 6 weeks after the Montgolfier brothers did the first ascent in a hot air balloon. So around about this time, scientists were starting to work out enough about how the properties of gases to work out that hot air has less dense than cold air, and so if you fill up a balloon with hot air, that should enable the balloon to float, and sure enough it did. And so the Montgolfier brothers, I think first of all they set up a sheep and a duck, and then later on they sent up themselves in the middle of France to huge acclaim. And then just very shortly after that, Charles, who was a chemist and knew about this reaction of things like zinc with acid, was able to make lots and lots of hydrogen. So he had these big tubs full of acid, and there were guys throwing big lumps of metal into them, making huge amounts of hydrogen, which filled up this balloon. And they were able to fly again out of Paris. And so this was the start of hot air ballooning, but it's also the start of manned flight. And so you could argue that's kind of a significant point in the history of society as we know it. A lot of you wouldn't have probably flew into Dunedin over the weekend. All of that idea that you can get around the place by flying started with these guys back in the late 1700s. It should be pointed out that another thing that we know about chemistry is that chemistry has a very love-hate relationship with the public at large. Everyone, if they think about it enough, will realise that chemistry is really important to their lives, but they're also very quick to blame chemistry when lots of things go wrong, and chemistry is perceived as being this rather scary thing. This is what happened to one of Charles's first balloons. Didn't have people in it just as well, but it flew off and out into the French countryside and was chased by peasants who attacked it with pitchforks and knives and destroyed it. All right, so already chemistry is getting offside with the public at large. The start of the ballooning thing in the late 1700s, not coincidentally, was right about the start of the time when chemistry started becoming a science as we would understand a science to be. Around about that time, and it's really interesting, about late 1700s, lots of people were starting to do really important groundbreaking experiments to actually start working out what elements were and what compounds were and what things like stoichiometry was. And in the middle of all of this was this guy who is kind of credited with being the father of modern chemistry. It's not completely true that he was the single guy who rescued chemistry from alchemy, but he was certainly one of the big names in it. So this guy Lavoisier, who was a Frenchman, there was a lot of British guys, a lot of French guys. And the British guys, as it turned out, were all generally wrong. And Lavoisier showed that, in fact, they were all wrong. And so there was the so-called French school of chemistry, which the Brits didn't like for a long time until eventually they had to accept that it was right. And so Lavoisier did things like he actually did reactions where he weighed out how much of the reactants he put in, and he weighed out how much products he got out, and he was able to show that the mass of everything that went into a reaction was the same as the mass of everything that came out. Sort of stuff where you would think is very fundamental, but it was very, very cutting edge at the time. And indeed, speaking of cutting edge, you might note the date that he died. Does anyone recognise that date? 1794, Paris? No? It's the revolution, yeah? He was also a tax collector, so he got his head cut off. Quite young, and so he probably could have done a lot more very interesting, important chemistry had he not sort of suffered at the hands of the previously mentioned peasants, perhaps. So 1790, give or take, was when chemistry started becoming the science that we understand it to be today, where people understand things like stoichiometry and elements and compounds and that sort of thing. And so you might think that that's what, 320 years ago. You might think, well, that's all done now. Everyone's kind of got chemistry sussed, let's move on. But just to show you that that's not true, this was out of a paper end of 2009. And I'm sure if I'd gone looking, I could have found plenty of papers more recent than this, but this is just an example. So there's some guys at Carnegie have found, for the first time, they found that under high pressure, you can make a unique hydrogen storage material where you can take xenon. So xenon is this stuff up here. Right on that far right-hand part of the periodic table, which, as we will see, is normally characterized by having elements that don't really do anything. They're quite happy as they are. Well, these guys have made the first xenon hydrogen compound. And in the process discovered an entirely new way of bonding elements together to make molecules. Right? This was like 14 months ago. So even though chemistry has been around for 300 odd years, there are still new discoveries being made all the time. And there's various different reasons why this is the case. A lot of it is driven by the fact that increasingly people are realizing that even though you can argue that science is responsible for getting the world into the situation it finds itself for things like fossil fuels and pollution, it's going to be science that's going to get us out of it as well. And so there's lots and lots and lots of scientists who are spending their research careers trying to come up with new ways of doing things like making energy from solar, transforming solar energy into electricity, trying to find new ways of dealing with pollution, trying to find new ways of making new drugs. There's guys in this department here who are working on new ways to make solar cells. I actually came across something on CNN on the weekend. Heaven help us, CNN were talking to a guy called Gretzel, Professor Gretzel from Switzerland. Yes, who is making new solar cells out of effectively blackcurrant juice and white paint. Right, you can do this. It's very clever. You don't, and there's a point where you don't even need to have the sun on at the time. You can do this inside. Although then you've got lights which are already requiring electricity. I didn't quite understand that, but nonetheless, white paint and blackcurrant juice you can make solar cells out of now. Right? Here's a molecule. It's a big molecule. This is not going to be on the test at the end. This is a molecule called Taxol. Have we heard of Taxol? Some of you will have heard of Taxol. Taxol is a breast cancer drug. And probably is the leading breast, as far as I'm aware, it's still the leading breast cancer drug that's prescribed these days. And that's what it looks like. And if you've done any chemistry at all, you'll recognize that's kind of a big molecule, kind of a complicated molecule, but nastier than acetic acid. This molecule was originally found in this tree, not the person, but the tree, which is called a Pacific yew tree. And what people do, there's this field of chemistry called natural products chemistry, where people go around and they take samples of plants or trees or insects or sea anemones or microbes or whatever, and then they milkshake them up, and then they pour that milkshake in with some cancer cells and see if the cells die. And if they die, then they start going about the process of purifying the milkshake and isolating out which particular molecules are the ones that are toxic to the cancer cells. And so a process like that led some guys back in the 60s to discover this molecule Taxol. They then had to work out the structure of the molecule because you need to be able to make it. The problem with Taxol is that it's an extremely good drug against breast cancer, but it comes out of the bark of the trees. And so you can't go and take all the bark off the tree. I think one tree gives you enough drug to treat one person, but if you take all the bark off the tree dies. Then you have to wait another 100 years for another tree to grow. So that doesn't really work. So it's really unfortunate in this case because the drug that you want is in the bark. Sometimes it's in the leaves, sometimes it's in a plant that you can grow really quickly out in a farm somewhere and then you're okay. But in this case, that was no good. And so what people had to do is they had to work out how to make that molecule from scratch. And that is a big job, and in the end there were about 3 different groups who published a way of making that sort of independently, all published at about the same time. And in each case, it was about 40 or 50 chemical reactions. So you start with a thing, and you do a reaction, and you turn it into a thing, and you do a reaction, and you turn it into a thing, and so on, and so on, and so on, and so on. Probably, I don't know, 10 years' work for a research group of 20 PhD students. That's all they did for 10 years, was working out how to make this molecule. And so what you end up with is you end up with a way of making the molecule, which is fine, but then if you want to do that industrially, it becomes heinously expensive because it's just so hard to do. And by the time you've done 40 steps, you'll start off with a kilogram of compound and you'll end up with like 3 milligrams of stuff at the end. So it's really expensive to do. And so what they then in the end discovered was that you can make part of this molecule, all the really nasty looking bit on this side, I believe, you can get that out of the needles of the tree. Right? So the tree has needles like a pine tree and they all fall off every year. You can harvest those and you can get most of the molecule out, and then you can do some chemistry on that to make the Taxol that you need. Right? So it's kind of halfway. You let the plant do it make half the molecule, and then you do the rest. Right? And so that's why Taxol can still be used. If it was just out of the bark, they wouldn't have been able to use it at all. Why am I telling you this story? Well, it makes a few points about where chemistry is at the moment. First of all, there's a lot of chemistry that goes on just to learn how to make new molecules, right? There would have been lots and lots of new, previously unreported types of chemical reactions that had to be developed, new types of catalysts to make those reactions happen that would have had to have been developed to make that molecule from scratch. And so in the process of learning how to make that, we learn a lot more about how chemistry works and how reactions work. The other thing is that even though it took a group of 20 research students, say 10 years to make this molecule, the Pacific yew tree does it every day and doesn't think twice about it. And so another really important thing to realize about chemistry is that out in the real world, you have plants and you have animals, and indeed you have yourselves, who will all the time make molecules that we haven't got a show of making in the lab. So even though we're 320 years in past Lavoisier, and chemistry is supposedly this mature subject that we're celebrating in the International Year of Chemistry, there is still an awful lot of chemistry that we don't know how to do. And we're getting pretty smart at it, but there's still no way that you can make that in any way like as simple and straightforward a way as the plant will. Right? They have enzymes. They have all sorts of very fancy, sophisticated processes that they can do to, and the thing is that they don't just make this mindlessly, but they only make it when they need it. I don't know why the tree needs this molecule, but oftentimes in plants you will get these things as a deterrent. If they see an insect coming, and then they'll make a molecule that makes the plant taste bitter so the bug doesn't want to eat it or something. They will make these molecules at will. They'll say, oh heck, there's a bug coming, let's start making this molecule. Make the molecule, and then the bug goes away, and then they don't need it anymore, and they decompose the molecule and move on. Right? It doesn't take them 10 years to do it. They just do it like that. And we can't do any of that stuff yet. So there's lots and lots and lots of chemistry that we still need to learn how to do. And so it's still kind of a cool subject. Yeah? Okay. Fundamental to the whole thing is the periodic table. And I have to apologise, there was a printing error. Not of my making this time, that one in your little folders was. But in the back of your lab manual there was supposed to be a periodic table, and there's not, is there? There wasn't the proof, I promise you, there wasn't the proof, but somewhere between there and when it finally arrived, it got lost. So I will have to get you all a copy of the periodic table. You will not need to learn the periodic table for bridging chemistry. Yes? How many of you at school got taught to learn the first 20 elements? How many of you at school got taught to learn stupid things like electronegativities of the elements? See? Honestly. It's in every chemistry book you will ever pick up, except for the lab manual. Every chemistry textbook you ever pick up will have a periodic table in it. It's on the walls of all the rooms. You do not need to memorize the periodic table. You don't need to memorize molar masses. You don't need to memorize electronegativities, because we will give them to you. What we need you to do is to recognize that you need to go and look them up at the appropriate time and to know what they're telling you, but you don't need to know the numbers. Yeah? So, the periodic table. The periodic table has a whole bunch of really important stuff in it. And one of the things that's really important about it, and we're going to come back to this in a second, but it was hinted at in the video, is this business about how the elements are arranged in these rows. Where's my green stick? So here's zinc, that the video was about, and as he said, zinc comes above cadmium and mercury. Now normally, what you find in the periodic table is that these rows of elements that go down all have similar chemical properties. In fact, this is how the periodic table was first come up with originally, back in the 1860s, that zinc and cadmium and mercury, even though you might think about zinc being the stuff you have on your roof and mercury being this crazy toxic liquid, in terms of their chemical properties, they're very similar. And in fact, this is why, he didn't say this on the video, but this is why cadmium is so toxic. Because he said that zinc's in all these different enzymes you have in your body. Well, if you get some cadmium into you, then what can happen is that the cadmium can replace the zinc because it's very similar to zinc, right? So if you've got a particular part of an enzyme that likes to have a zinc, then because cadmium is very similar, the cadmium can get in as well, but then it can completely screw everything up because the enzyme won't work quite the same way with the cadmium there, and then all your biological processes will stop working, right? And same with mercury. But in general, as you go down, then you find that the elements have similar chemical properties to each other. As you go across, then you find that there's a general change in the chemical properties. And we can understand all of this by understanding fundamentally about how the different atoms of the different compounds the elements are put together. And that's what we're going to start looking at today, and we're going to come back to in the third week of the course. All right? A couple more names of people. Obviously, I'm not going to test you on any of this, but in theory it's interesting. This is John Dalton. Again, look when he was born, 1766, 1844, so around about this late 1700s, early 1800s. Another key guy in the whole development of chemistry. He was the guy who, amongst a whole bunch of other things, he was the guy who sort of reinvented the idea of an atom. Atoms had been proposed by the Greeks way, way back. But then this guy called Aristotle, you'd have heard of him, he decided there weren't things called atoms, and because Aristotle kind of was the man, everyone stopped believing in atoms for about 1,000 years, 1,500 years, long time. But then eventually experiments led people to conclude that in fact there probably must be atoms, and one of the big drivers of this sort of going back to this idea was Dalton. And so he came up with this idea of using little symbols to denote the different atoms, and importantly this idea that compounds were made up of combinations of different types of atoms, right? So I can't remember how this works. I think this one's water, and they'd worked out by then that water consisted of hydrogen and oxygen, right? So here's hydrogen, and here's oxygen, and then this is water. Now this is an H and an O. They didn't know at that stage that it was H2O. They just knew that it contained hydrogen and oxygen. And so he gave this little symbol for having an oxygen and a hydrogen together somehow, right? And if you knew what the other ones were, you could work out some of this. There's 20 different elements up at the time. You know, the periodic table as we understand it at the moment has got, in fact this is actually an old one, There's actually 111 officially named elements now. But back then there was only about 20, and these were the things that had been around forever, like sulfur and carbon and, well, see, not nitrogen and oxygen, because nitrogen and oxygen only just very recently been discovered at this point, so not necessarily those, but anyway, only a handful. And so there was this little handful of elements that were known. I keep saying element. I'm going to come back and define what that is shortly, but just bear with me. It was then Mendeleev, well, it's Mendeleev who was credited with being the first person to take all these different elements and look at their chemical properties and say, is there some way that we can arrange all of these together so that we can group the atoms that have similar chemical properties with each other and come up with what became the periodic table? In fact, the story goes that he took like playing cards and he wrote on the playing cards the element's name and their chemical properties, and then, the way the books say it, he played patience with them, right? So he moved all the cards around trying to get them together so that there was keeping the elements that had similar chemical properties with each other in these rows. And what he came up with was this, which if you turn it around a little bit, is just the periodic table that we know now. There was other guys who came up with the same sort of idea. There was a guy called Odling a bit earlier. There was a guy called Newlands, especially, who pretty much came up with the same thing. But Newlands moved from like Oxford to Cambridge or something, and he never unpacked all his stuff. And so he had basically the manuscript for reporting the periodic table in a box. But by the time he finally unpacked the box, Mendeleev had published and beaten him to it. Yeah? C'est la vie. But the thing that Mendeleev did, which was really important, was, see in the middle here, there's a couple of question marks. And there's a question mark there as well. Yes, there's those 3 question marks. What he did was this. He was so sure that the way that this ordering of the elements together based on their chemical properties, he was so sure that that was the right way to go, was that when he did all that, he found that there were some gaps. Right? So he'd have like a row of, say, fluorine, chlorine, bromine, iodine. Right? And so that all worked. He had these 4 in a row that all had these similar properties. And then oxygen, sulfur, selenium. But at some points, he found that when he tried to order the other elements that way, there were gaps. His system broke down. And so other people would have said, oh, maybe it's not right. Oh, maybe I'm just wrong. And leave it. What he said was, no, the reason why there's gaps is because there's other elements that go in there, but no one's discovered them yet. Which was very brave and very clever of him. Because that's kind of, it seems to me, the reason why he's now the one who's credited with the periodic table. Right? Because he was the only one who did that. And sure enough, down the track, some of these missing elements were discovered, and when they were discovered, they had exactly the properties that Mendeleev predicted they should have to go in that particular part of the periodic table. Yeah? Okay, so the periodic table then is a collection of all the different types of elements that are known. So what then is an element? So if you like, suddenly we're into the whole, we've finished the history stuff and we're into kind of the stuff you need to know. There's lots more stories about Mendeleev, but I can tell you those later if you want. You don't need to know those. Okay, so we get to the important stuff, and now we have Rutherford there, so that's good. An atom, up until the early part of last century, was thought at best to be a little blob that contained 2 types of things, protons and electrons. And these had been discovered earlier on by various other scientists. They tended to be physicists. They'd worked out that atoms were composed of things that had positive charges and things that had negative charges. And the things with positive charges were called protons, and the things with negative charges were called electrons. Right? Don't really want to get into where that came from because that's kind of physics, but nonetheless, until in the 1910s, there was this thing called a plum pudding model, which said that an atom was composed of protons and electrons stuck together somehow, and so the idea was that the electrons were like the plums in a plum pudding. Yeah? You have to kind of think 100 years ago in Britain, but